So we're picking up where we left off on Thursday. We were talking about the Poisson Pmf, and we had already answered a couple quick questions, right? So these questions right here, where we're talking. We know some average number of events for a span of time, or an area, whatever it might be. And sorry, one sec. Oh, okay, good. So we have an average. We have an expected number of values, and it turns out that this lambda here is also the mean. Lambda is the mean in a Poisson distribution, which is pretty convenient. And given some lambda, given some expectation for a certain span of time, we can extrapolate that out to other spans of time, given the constraints that we established, that the rate, the frequency of the event occurring is consistent, the events are independent of each other, and they're identically distributed. Those being the main ones. And yeah, we can establish some lambda, right? 10 people in an hour, and we can ask a different question. Well, what is the probability of 12 people in an hour? Or in this case, 23 for one image. What is the probability of 35 for two images? And we can just adjust the lambda accordingly. So that's pretty straightforward. And, we coded out the Poisson Pmf. What we see here in Poisson is E. And we can think about Euler's number as being something like a decay factor. And it is an emergent property as we increase the number of trials of binomial and hold lambda constant. So that's something that we can demonstrate in code, and that's the next couple slides will cover that. So as we take n towards infinity, the result of taking n towards infinity of a binomial distribution, if we hold other things constant, is that our probability will tend towards 0 as long as lambda is constant. And we can think about our lambda, our expectation, right, our mean, in a binomial distribution. Well, that's just the number of trials multiplied by the probability of success on any given trial. So if we make these two things equivalent, if we make lambda equivalent to NP, then we can kind of rework the binomial PMF to contain it can contain lambda, and we'll see that as such, right? Because if lambda equals NP, then clearly sorry, my drawing tablet's flickering a lot. 1 second. See if I can repair this. Well, I can still draw, even though it's flickering. Okay, so if we think of lambda, this is hard to do. If lambda equals NP, then we can rearrange this. We can replace P, right? We can say P equals lambda over n, right? Lambda over n. Okay, the drawing tablet might be out today. Okay. We'll just have to work through this slide as it is. And we can rearrange this. We can rewrite the binomial PMF in this form, where we have, instead of the probability here, we've got lambda over n. And I think that this makes it pretty clear that our probability tends towards 0 as we increase the value of n. So, n is going to go up. We go from 10 trials to 1,000 trials. then our probability is going to have to decrease. Although we haven't changed, if we think about there being a time box, right? A time box for those trials, we haven't really changed our lambda, okay? And what we should see is the emergence of specific probabilities. And I'm going to go over to our code to do this. This is demonstrated in the slides, but I think walking through it is helpful. So let's see. Are we importing? Yeah, we're importing math and factorial, which we need both of those. Okay. So we're going to need combinations. So n choose k. And I'm just going to return factorial of n. Oops. Divided by factorial of n minus k. Multiplied by the factorial of k. And I'm going to cast that to an int. It's not entirely necessary, but I do it anyway. And then we've got the binomial PMF, n, k, and we'll set p to 0.5 by default. And we'll return the combinations of n choose k multiplied by p to the k multiplied by 1 minus p to the n minus k. All right. So, and we have the Poisson PMF above. So those are the three things we're going to need. So I'm going to start with a fixed n, with a fixed lambda, and I'm going to start with n equals 1. So let's do lambda of 10, and let's see if we can see the emergence of the expected probability for k equals 10 in a Poisson distribution. So this is something like 0.12503, something like that. Okay. And what we can do, we can just do this with a simple for loop and look at some output. So for n in range, we'll start at k, and we'll go up to, let's go up to 10,000. And I'm going to print the result of binomial. So I'm going to round this, the binomial PMF, n, k, and here I'm going to set our probability to lambda over n, right? So this is our p equals lambda over n, and that shouldn't be lambda, it should be LMBDA. Okay. And I'm going to round this to 7 places. Okay. So here, if I, like, we're going to see a consistent value here for the Poisson PMF, which takes lambda and k and no fixed probability. So we should see that we're approaching this second statement from the results of this first statement. Let's see, is that okay? There's something weird there. What is going on? Oh, I see. Missing a closed parentheses. Okay. So I think that's all we need to do there. And I'm just going to put an extra space here so that it's clear each iteration we do. Oh. Okay. Oh, I see. We want to round to 7 places. All right. And I'll bring this up here. So notice when we're doing this, the result of this binomial function is moving toward Poisson, even though I labeled it. Let's do this. Try that again. All right. So notice we're getting closer and closer from binomial to the result of the Poisson, the result from the Poisson Pmf, right? And we can try this with any values of lambda, any values of k, and we're going to be able to see this. In fact, we could build a dictionary that looks for these differences, and where we try to figure out to what degree of samples, right? If we're looking at 10,000 versus 100,000, right? How many iterations it actually takes to achieve the precision that we have on our computers, right? We could do that. I don't want to do that, but we could do that. So let's try this with some other values. Let's try lambda of 100 and k of 10. Let's see how that goes. Oh, well, that makes sense because we're getting really close to 0 with 7, with rounding at 7. So let's try lambda of 20 and k of 10. And so here, notice that our result of the binomial PMF is increasing. In the previous one, it was decreasing, right? It was decreasing down toward Poisson. And now we're increasing up toward Poisson, and the rate of increase is actually slowing down as we get closer to Poisson. So we don't quite get there in 10,000, but we're doing pretty okay, right? We're getting fairly close. And to be clear, the reason I'm doing this is to try to drive home this point that you can verify things, right? If somebody says, well, this is what if you increase n and hold lambda constant in a binomial distribution, as you increase n, you tend toward the Poisson distribution. You can verify that, right? You can use code to verify that, and you should. You should. For theoretical, for understanding the theoretical underpinnings here, you should. But also, you should do this in practice in general. You want to just verify that something is doing what you expect it to do. Okay. And that's just that code block. Yeah, and I think this was posted last time in the Slack. If you want to look at our general analytic approach applied to the emergence of Euler's number, this playlist has like 4 videos on that. The first video covers binomial and Bernoulli, or Bernoulli and binomial as it relates to E, and that is in direct relationship with the Poisson distribution. So feel free to go through those. Okay. All right, so here's a quick breakout. We have what we're going to consider to be a Poisson phenomenon here. Cars passing by an intersection at a certain time of day or year for the duration of a fixed amount of time will likely follow a Poisson distribution. So the question is, a given intersection will have on average 15 cars pass through in 10 minutes. What is the probability that 20 cars pass through in 15 minutes? So I'm going to put 3 minutes here, and yeah, go for it. You're going to need to transform lambda here, because your lambda, initially you think of your lambda as being 15 cars for 10 minutes, but you do have to transform it for 15 minutes. Okay, let's walk through how to solve this. Okay, so our lambda here is going to, well, the information that we have here, lambda is 15 for 10. So we are increasing from 10 minutes to 15 minutes. And we can just think about this as, well, this is just an increase of 15 over 10, right? And that's a way we could do that, and we're going to get a corrected lambda. The k that we're looking for is 20, and when we get down to this, it's just the Poisson Pmf of lambda and k. And if we print that, it's going to be something like 0.0769 roughly. And so what does that mean? That means that given an intersection, given this intersection where we expect 15 times 1.5 cars to come through, the probability that 20 cars come through in 15 minutes is going to be 0.0768 or 0.0769 roughly. Okay. Okay, so sure. Yeah, the corrected lambda. I'm sorry my tablet's not working right now, because it's really kind of simple to just draw it out. But yeah, if we're looking at this, let's go back up to here. So if we're considering 15 cars in 10 minutes, well, we're increasing from 10 minutes to 15 minutes, right? And so if we're expecting 15 cars in 10 minutes, then in 15 minutes it would be 15 times 15 over 10, or 15 times 1.5. And it's really just we're scaling up our span of time, and we need to scale up our expectation to meet that. And this is really at the heart of most Poisson problems that you're going to encounter. There's going to be some modification of lambda, right? Lambda, we expect, so lambda is a frequency times a span of time, right? So if we're thinking 15 cars in 10 minutes, well, what would be our expectation for the number of cars in 5 minutes? Yeah, 7.5. Exactly. So if we're increasing the amount of time, like if it would be obvious if we said, well, 15 cars in 10 minutes, how many cars in 20 minutes? We would say 30. But in this case, we're modifying it by 1.5. So 22.5 cars in 15 minutes. Does that kind of clear that up? This is sort of the beauty of Poisson, really. It's that, given these constraints, we have a fairly mathematically simple way of determining probabilities. And if you've done a fair amount of, like if you've gotten into quantum physics, Poisson shows up everywhere. It shows up everywhere in astronomy and in astrophysics. Because we have these things where we assume some kind of independence, right? And Poisson just sort of emerges out of it in a lot of places, which is pretty amazing. Okay, so the Poisson Cdf, I didn't put any code in here, did I, for how we think about the Poisson Cdf? The Poisson Cdf is simply the summation from 0 up to and including k of the Poisson Pmf. I really thought that I put in a mathematical representation of this, but while you're coding this, maybe I'll draw it up so that we can walk through it a little bit. But yeah, so this is going to be pretty straightforward. You're just going to call out to the Poisson Pmf and construct the cumulative density function for all values 0 up until k. Okay, so I'm going to put 5 minutes on the clock. If you have any questions, go ahead and ask them. And yeah, this is a simple accumulator pattern. Okay, so let's go ahead and code this. This is just Poisson Cdf, and we're going to pass in Lambda, and I'm going to call this k high, just the inclusive high value of k. And we're making a Cdf, so I'll just say for k in range, and we're going to go up to, from 0, right, up to k high plus 1, because we're including k high. And then Cdf is going to be collect, or is going to be incremented by the Poisson Pmf for lambda and k. When that's all done, we can return the Cdf, and that should work. So let's, I'm going to print the Poisson Cdf for lambda of 10 and k of 10, and see what we get. Oh. Okay, so a little over half, which is what we would expect, given the expectation or the mean of 10. Okay, so I'm going to go ahead and paste this into the Slack. Although there are a lot of other working solutions in there as well. And yeah, everyone should have the Poisson Pmf on hand too. Okay, great. All right, so here's a quick CDF problem. I'll put 3 minutes on the clock, and yeah, think about what's being asked here and do your best to solve it. Okay, so this one can be a little tricky. You know, we know what our lambda is, so let's first think about that. Our lambda is going to be the same lambda as we have up here. And why don't I also paste in this question? Okay. So we're wondering what is the probability that more than 15 cars will pass through in 15 minutes? Okay. So recognize this more than, right? So we can simply do 1 minus the Cdf of 15. Because it's going to be 0 cars, 1 car, 2 cars, 3 cars, all the way up to 15 cars. And then we take the complement of that. Turns out that Poisson goes off to the right infinitely, right? Like we can have an infinite, theoretically an infinite number of cars pass through this intersection within some span of time. So we don't have a very simple way to, you know, sum up from 15, but we can do 1 minus the Poisson Cdf of lambda and 15. And this should give us the probability of all cars, you know, of any number of cars greater than 15. So let's see what that is. 0.936, is that what other people are getting to? Huh. Let me just, okay. Okay, great. Perfect. All right, so we're going to, this is going to be a little bit of a longer breakout, but we're following that same pattern, right? The same pattern we've been doing where we pack values into a dictionary. So this is going to be the Poisson Pmf Dictionary. You're going to pass in a lambda. The lambda is going to stay fixed. You're going to go from a low k to a high k. And your dictionary should get packed in with where the keys are all values from low k to high k inclusive. And the values are the probabilities associated with those values of k. So I'm going to put 6 minutes on the clock. And yeah, this, if you need to reference something that looks like this, go look at the last few binomial PMF dictionary things that we were doing. This should give you a good sense of this. Okay, let's walk through this. This is following, the same pattern that we've been doing, where we pack things into a dictionary, essentially, right? So this is kind of our analytic pattern. We take some phenomenon, and we, given some input, we get some output, right? So lambda, we're going to go from low k to high k, and we're going to set a dictionary. Now, from here, we can just do a for loop, right, for each k in range from low k to high k inclusive. I'm just going to say d sub k gets the Poisson Pmf for lambda and k. And at that point, we can return the dictionary. So from here, we can just output this, right? So the Poisson Pmf Dictionary. And why don't we do this with lambda of 10, low k of 0, and a high k of 20. And then this other pattern, this pattern should be familiar as well, how we're outputting things from these dictionaries. So for kv in d.items, let's say print k and v. And if we look at this, this is the kind of place where maybe we would want to round just because we're trying to get some display output. But whoa. But this is an interesting little facet of Poisson. The probability of 9 events is the same as the probability of our expectation, 10. And if you run this with a bunch of different lambdas, you'll see that this is something that occurs pretty often, right? If you put in a lambda of 20, then 19 and 20 are going to have the same probability. Kind of cool. Or essentially the same. There is a point where that isn't true anymore, but that's something that you can investigate. Okay. So here's, I think this is our last little bit here. Let's say you're observing a phenomenon that follows perfectly a Poisson process, right? Something out, I don't know, images of stars, right? Could be anything. So given a certain number of observations, let's say you have 10,000 images of stars, how would you determine how many events to expect for each value of k, given lambda is 10, low k is 0, and high k is 30? And I'm not asking you to code this, but how would you do that? Right? You have 10,000 observations. How would you fill in your values of k? Your counts for each value of k. So your current Poisson Pmf Dictionary gives you the probability for k events. If you have a certain number of observations, what is the projected count for k events? So this may not be immediately obvious, but you can just multiply the probability by the number of observations. And if we want to do this in code, yeah, exactly. The probability times the number of samples, or number of observations, however we want to think about that. So I'll code through this. We can just grab this prior function, actually, and adapt it slightly. So let's call this Poisson counts, and we can give it a low k and a high k, and a number of samples of 10,000. Is that what we were talking about, 10,000? Yeah. So all of this is the same, except now we can multiply this probability by num samples. And we probably want to round this and kind of purely round it, right? We're going to round it as if we cannot have a fraction, right? So if we look at this, and I'll just grab that whole thing. If we look at this, what we're going to see is some kind of information loss. And I think this is an important thing to just point out. Notice that we don't have any count for 0 events, right? So if it's an improbable event and we're out there making an observation, in any given trial of this sampling process, we might miss out on the least probable of these. It doesn't mean that they don't have representation in the theoretical distribution, or if this is an observed phenomenon out in the universe, doesn't mean that just because something hasn't happened, it won't happen or it can't happen, right? There is some probability that it can, but that probability, at least is fairly unlikely for that to happen within 10,000 samples. Now, if we were to increase this, right, maybe that would change. Let's see. So now we do have a count for 0. And something that might come up, let me just say it like that. Something that might come up is, at some point, you might be given some data, and you might be asked, well, does this data follow any known distribution, that any common distribution? And you might be looking at some kind of just counts of something happening given an input. So given this input, this value of k, and the observed counts, you could compare this Poisson distribution, counts of a Poisson distribution. You can compare this to the actual phenomenon, and you can subtract. You can take the mean squared error here. You could subtract the observed from the theoretical and square it and look at your error. And that's something, and take the root of it and look at your average error. And you might be trying to optimize for the lowest root mean squared error, for example. That's a common thing we do if we're trying to figure out, does this phenomenon reasonably follow a Poisson distribution? That's something that isn't it's a nice first look sometimes at some data, because if you have data that actually does reasonably follow a known distribution, it saves you a ton of work, right? And we've got these closed formulas through which we can analyze it. This is I think we do this kind of thing a lot with Poisson, because Poisson is so convenient, and there's so many phenomena that look like Poisson, right? That sometimes if we think a phenomenon is Poisson-like, we'll just use Poisson, and we'll say, well, this is reasonably applicable here, and we might try to quantify, error in regards to it. But even still, we might use it because it is so convenient. Okay, so that's it for Poisson. And we're going to have a bunch of Poisson problems when we do our TI review day, which will be the last day of class, not next Monday, but the Monday following. We'll be, just coming up with, 10, 15 Poisson problems. And, those are just for you to have some extra practice. We'll invent them ourselves, though. So I'll have you write the Poisson problems when we get there. Yeah, so that's it for Poisson. We're going to cover the geometric distribution. We might get through that today, and if we do, then you'll be with Clark on Monday. Otherwise, I'll finish up geometric and get into the normal and exponential distributions on Monday. But right now, let's take 6 minutes break, and I'll see y'all back here, and we'll get started with geometric.
1 minute remaining. Time's up. 6 minutes have elapsed.
Okay, let's get back to it. So the geometric distribution is really simple to understand, and it can also get a little confusing because we have two different PMFs for it. We have two different forms of the PMF, and I'll talk about that very shortly. So simply, the geometric distribution is going to, let's pull up the slides for this before I get too far. Oh, there it is. Okay. So we're going to relate geometric back to binomial, right? Kind of like what we did with Poisson, except geometric looks a lot more like binomial than Poisson does. We do a lot less in the way of transformation of it. So to think about this, I'm going to, unfortunately, my tablet's not working because I think this lends itself really nicely to things being visual. But let's think about this just in terms of successes and failures, right? So we have some Bernoulli trial, right? So Bernoulli with a probability of 0.5. If we think about successes and failures, we can think about how many failures up until the first success. So maybe we have 2 failures and then a success. Maybe we have a failure, then a success. Maybe we have a success. Maybe we have, a failure and a success. Maybe we have, even though it's unlikely, maybe this occurs one time, And so if we think about this, we can relate this not only to binomial, we can relate it to just a simple string of probabilistic outcomes, right? So what is the probability that we have 2 failures before our first success here? Well, first let's think about what is the probability of having this outcome, right? This is going to be 0.5 times 0.5 times 0.5 for that specific outcome if we're flipping a coin 3 times. So the question that we're asking with geometric isn't how many successes. We're only going to have 1 success. What we're really asking here is how many failures up until the first success. And in this case, K is going to represent K represents the number of failures. And we can either do this before and including the first success. And this is where we get into the 2 different versions of the geometric So here's the kind of question we might answer. What is the probability of having to flip a fair coin 5 times before a flip that results in heads on the 6th flip, right? That's fairly improbable, as it turns out, but this is the type of question. How many times might you observe a certain chip before it fails, right? That's a similar kind of question. Okay. So there are 2 forms of the geometric PMF. We have a form of it where we calculate the trials, the number of trials up to and including the first success, and we have another form where we calculate the number of trials before the first success. The probability that you get out of this is going to be the exact same probability if you're doing this correctly, okay? So if we're talking about what's the probability of 5 tails before you get your first heads, and we plug that into here, well, 5 tails is 5 failures, right? And 6 would be your 6th trial. So up to and including would have a K of 6. Whereas if we're considering the number of trials before the first success, then 5 tails, right, that is your K. Its K is 5 if we're talking about before the first success. So it's just 2 different ways of thinking about the same problem. There's some nice convenience method. We call these moments, right? The mean is a moment. The standard deviation is a moment. Kurtosis is a moment. There are these statistics that we call moments, or these parameters that we call moments. The expectation for the geometric distribution is just 1 over p. That's really, really convenient. So if we're thinking about a coin flip, 1 over 0.5 is 2. So we expect to get heads within 2 coin flips. That sounds reasonable, right? That seems fairly straightforward. Now, this is just 2 different forms, again, of the same idea. Okay? Although, let's think about this. 1 minus 0.5 over 0.5. Well, that means that our expectation is going to be 1, right? So that's our expectation before the first success. We would expect to flip the coin 1 time before our first success. Like, it's the same statement, but we're just thinking about it from a slightly different angle. Again, we have a simple variance formula. We're not going to cover these other moments here, really. We're just going to think about this in terms of accounting for these 2 different forms. So I'm going to have you code the geometric PMF function, and you're going to have 3 parameters here. You're going to have the probability, the value of k, which is the number of failures, either inclusive or exclusive of the first success, okay? So you're going to have a switch here, and that switch is going to lead you to implementing both these forms depending on whether the switch is true. If the switch is true, then we're going to be inclusive of the first success, and you're going to use this formula. If the switch is false, then you're going to be exclusive of the first success, and you're going to use this formula. So something that you might notice, maybe a couple of you will notice, there's a way to write this in 1 line without using an if statement. But if you don't see it, definitely use an if. If inclusive is true, do this, else do this other thing. But there's a way to do this without the if statement. So I'll leave that to you to figure out. All right, I'm going to put 4 minutes on the clock, and yeah, go for it. Okay, so let's go ahead and code the geometric PMF. So the probability of a success on any given Bernoulli trial, K, which is the number of times up to or up until and including the first success, and then whether or not we want to be inclusive of that first success. So by default, I'll set that to true. Now, the one-line way to do this is just return the probability times 1 minus p to the k minus inclusive. And that's because we can think of Booleans as being ones or zeros, or trues or falses. We can use them in just normal integer math. So we can do it like this, or we can set it up with an if-else. So if inclusive, then we can return p times, well, really something that looks almost exactly the same as this, k minus 1, and then else return 1 minus p to the k, right? So either of these ways works. If you're thinking more Pythonically, this line 3 works. If you're thinking in a more classic coding perspective, lines 4 through 7 work. Both of them work though, right? It's not really important which one of these you do. It's more important just that you understand, how to do this. Okay, so let's look at a quick problem using this. So you're flipping a fair coin. What is the probability that you get your first heads on the 7th flip? Now, what I'd like you to do here is put in the code for both versions of the function when you do this. So, yeah, so you're gonna put in your function calls and the answer for this one. Okay, let's just break this problem down. Oops. Okay, so you're flipping a fair coin. What is the probability that you get your first heads on the 7th flip? Okay, so if we're thinking about this as being, if we're thinking about this as inclusive, well, then our k is 7, right? We're assuming a fair coin, so p is 0.5. K, I'm going to just set to 7 like this, and we can say the geometric PMF for p, k, if inclusive is true, right? If I set inclusive to false, then this needs to be k minus 1. And that's just because we're not including the first success. Oh, what am I? I'm running the wrong thing. There we go. And it looks like that's 0.0078125. I think that's what everyone else is getting as well. Okay. All right, so here's another one. You have a series of routers transmitting packets of data. There is a 0.99 probability that a given packet of data passes through the router. What is the probability that a given packet of data is lost in the 15th router? So I'll put 2 minutes for that. And yeah, go for it. Okay, so how do we think about this problem? Go ahead and copy this. So there's a 0.99 probability that a given packet of data passes through the router. And we're wondering about the probability of something being lost. So the packet not being successful in passage through the router. So we're going to take the complement of 0.99, right? So our probability here is actually 0.01. And our value of k is going to be, k is going to be 15, right? That's our 15th router in this series of routers. From here, we can just call, I'm just going to copy this from up here. We pass in p and k. Inclusive is true. That should give us the right answer. Now, if I want this, if I set this inclusive to false, then I'm going to say k minus 1 again. Now, why would you be asking this kind of question, right? What is the probability that a given packet of data is lost in the 15th router? Well, you could be monitoring packet loss in that router. And if your packet loss exceeds, just exceeds what the probability should be, right? If it exceeds what that probability should be from a given, initial location, you might use that as a way to diagnose that there's something wrong with the router, right? This is one means by which you might perform a diagnostic. Now, there are a lot of things that look like this, right? If you get into Internet of Things, if you get into kind of smart factories and things like that, where you have components that are sitting there and you need to have some kind of prediction to fail, right? You want to preempt the failure of a component. And if you can take enough observations, then you can build something that is essentially a geometric distribution. And maybe each trial is a given day. And you can map the lifetime of a component, and you can preempt the failure of a component so that you don't have to take your system down during industry hours. You can do it off time. So there are applications for this in the real world. It's not just, hey, here's this neat distribution, right? So let's run that. Looks like that's essentially 0.001. Is that what everybody else is getting? 0.008687? Yeah. Awesome. Okay. So here we have a really, really convenient CDF. Our CDF is a closed formula without a summation. So this is easy. We can just implement a CDF as this simple formula without summation. We can also perform the CDF as an accumulator pattern. So in this next breakout, I'm going to have you do both things. You're going to code the geometric CDF as an accumulator, and you're going to code it as using these closed formulas, right? So notice that is that's two different functions. Of course, they have this inclusive is true or false, right? You're going to code geometric CDF accumulator and geometric CDF closed. So yeah, go for it. And I'm going to go ahead and paste in the code for the PMF in case you need it. Oh, oops. Here, I'm going to give us just 2 more minutes on this so that y'all can try to get it in. Okay, so let's code this in 2 forms. So I'm going to call this Geom Cdf accumulator. We pass in P and K and the inclusive flag. Okay. And simple accumulator pattern. I'm going to set the probability, and then I'm going to say if it's inclusive, I'm going to start at 0. And this is kind of the tricky thing. If we're thinking about the 2 forms of this, there's the form where if we're including the first success up to and including the first success, then we don't have the option of a k equals 0. So we're going to actually start at k equals 1. And otherwise, we can start at k equals 0. So I'm going to say for r in range, starting at either 1 or 0 up to k plus 1. Proba is going to be incremented by the geometric PMF, P, R, and the inclusive flag. Now, instead of starting at, I could also just put in inclusive right there. So that works as well. And we can just return that probability and assume, my assumption is that that's going to work. And I'll code out the closed form of this, the closed formula form, which is just, looks like this. So P, K, inclusive is true by default. If it's inclusive, well, here's another case where inclusive is either 0 or 1, or true or false. So we can actually return, well, let's think about this in just a second. I'll code it out this way first. So return 1 minus P to the K, else return 1 minus P to the K plus 1, right? So in this case, it's actually, this would be k plus not inclusive. And here, this would be, we could just simplify this by doing k plus not inclusive, right? We could do that, and that would simplify this into a one-liner if we wanted to do it that way, right? So I'll do that, and let me just return that to its normal form. Okay, so let's see what this gets us if we run this with a few values. So let's do 0.5, and I'm gonna call both of these with both inclusive is true and inclusive is false. Oh, did I default this to inclusive is false? Yeah, I meant to do true. Okay. All right, so if we've got a p of, I don't know, 0.75, let's do something small, actually. 0.05, let's do that. So we're passing that in, and let's do a k of 7. Okay, let's do a k of 10. So in this inclusive is true, what do we need to do? What do we need to do here to make these inclusive falses work correctly? What do you think? What's going to make inclusive false work correctly? What do I need to modify there? Well, yeah, just k minus 1. All we need to do there is subtract 1 from k. And hopefully we'll get equivalent values when we run this. Let's see. Yeah, so all of those are coming out to the same result given that adjustment. And let me just make sure that this one-liner works as well. Let's see. Yeah, okay. So when you get down to this, you're not going to use the two different forms. You're going to use one of those two forms, and I think that's normal, right? You're going to choose which one you feel more comfortable with. You're going to stick with that. But depending on where you see geometric, someone is going to choose one or the other form, and that can be baffling if you come across it and you don't know what's going on. But yeah, just be aware there are these two different forms of it, and both are valid, and both will get you to a reasonable probability. Okay, so let's do this one. You have a series of routers transmitting packets of data. There's a 0.99 probability that a given packet of data passes through the router, through any given router is really what that should say. What is the probability that a given packet of data will pass successfully through 14 routers? And what is the probability that a given packet will be dropped before the 15th router it passes through? In other words, on or before the 14th router. So I'm going to put 3 minutes on the clock. And yeah, go ahead and answer those. Give me a thumbs up if you want another minute on this, or another couple minutes, if you're still trying to figure it out. Okay, I'm going to go through a quick solution for this. Okay, so this first question, it turns out this is a fairly straightforward, just probability question, actually. We've got a probability of success of 0.99, I believe, right? 0.99. Yep. And we're wondering what's the probability that the packet will pass successfully through 14 routers. That's going to be 0.99 times 0.99 times 0.99. It's really just 0.99 to the 14th power. So we don't need to use the CDF here, right? We can actually just use just the multiplication rule. Okay, so let's see what that is. 0.8687. Does that reflect what other people are getting? And this next one, the probability that a given packet will be dropped before the 15th router it passes through, right on or before the 14th router. I'm just going to use one of these. The probability that's going to be dropped is 0.01, right? And we can just use, I'll use the Geometric Cdf closed of, let's see, I'll be inclusive, so on or before the 14th router. So I'll set k to 14 and set inclusive to true. I could have put 13 in there and set inclusive to false. Either way is fine. Oh, where is that happening? Right there. Looks like that's 0.13. Yeah, 0.1312. If you want to give me, if anybody wants to give me corroboration on that, 0.13125 is what I'm seeing there. Okay, awesome, awesome. Okay, and so from here, so, you know, there's a couple simple applications of geometric that we're seeing here. We're going to take this into that geometric, well, there isn't that much time. I think there's time to code this. Yeah, why don't we do this one? Code the Geometric Pmf Dictionary, and we might call it there for geometric. We might not go through the sampling stuff because that's just another 20 minutes that we would tack on Monday. But I think, you know, definitely go through the remaining slides and take a peek at them. You know, how do we build a sampling process for geometric? Because I do think that's, I think that's worth looking at, but I don't think we need to go over that in class. It's just another example of, hey, here's a sampling process, right? Here's how this code works. Okay, so I'm going to put 4 minutes on the timer for this. Code the Geometric Pmf Dictionary function. Okay, I'm going to go ahead and code this, and I'll talk through it. So this is just, let me maybe make this a little bigger. So Geometric Pmf Dictionary, we're passing in a probability, the high value of k that we want to consider, and we're going to say inclusive is true. Okay, so instantiate a dictionary, and then say for k in range, here's where I'm going to use, again, that inclusive as our starting point, up to k high plus 1. And then d sub k is just going to get the geometric Pmf pk inclusive. We can return the dictionary, and I'm going to just compare these two. So let's do this for, we'll do it for 0.5. K high of, well, we'll do 10, and then we'll do an exclusive form. And for k, v in d exclusive, let's do that one first. The items, let's print f string of k and v. Oh. Oh, well, that makes sense. Okay, yeah. Common error. Need to do that. Oh, k high is what that's called. Okay. So this pattern is what you can refer to, you feel free to refer to it as a geometric decay, right? The probability is decreasing at a squared rate, right? And we can see that very clearly here. Now, I'm showing the exclusive form of this. Let's look at the inclusive form. And I'm just going to, I mentioned this before, but I just want to mention it again. In this case, we don't have a 0, right? Because we're talking about whether or not we have failure, how do I say that? Whether or not we have a success on the first try. That's what we're seeing in the inclusive form. Whereas the exclusive form is asking, well, how many counts before the first failure? So of course we can have 0, or sorry, before the first success. Of course, in the exclusive form we can have 0, because there are potentially we can get success on the first try, which would be 0 failures before the first success. So yeah, again, I just want to point out this pattern. This pattern does come up quite a bit, and you can use this construct, this dictionary construct, for approaching other geometric decays that aren't to the power of 2, right? You can see geometric decay in a lot of different ways, and you can do it in regards to a probability like so. So let's do 0.05, and we can see how this decay is much slower than it was with 0.5. Awesome. That's the lecture for today. Please go through the rest of the slides. Just play around with the code that's in there, especially regarding sampling. I think that's pretty interesting. And most of the sampling we did was with the binomial distribution. So we'll do some other sampling at the end. Oh, I guess we did it with combinations and permutations as well. Okay, yeah. But we definitely want you to know how to kind of do a simulation through sampling the way that I've done it in these lectures. We want to know that you can pack values into a dictionary in general, right? Okay. I think Monday and Tuesday Clark is teaching, and then we'll pick up with continuous distributions and conditional probability. Next Saturday will be kind of a machine learning class. It'll be kind of a crash course in machine learning, and then the Monday after that will be our wrap-up day where we go over a lot of things in regards to the technical interview. We'll kind of invent a new technical interview during that class. So stay on if you have any questions. Otherwise, have a great weekend, and I'll see y'all Wednesday at the latest.